Hello students, my name is Reni and this is a GCSE video. Today we will be talking about electrical resistance. What do you mean by electrical resistance? As you can see over here, it is written electric resistance is the measure of stopping electrons flowing. Let me give you an example. You can imagine yourself in an airport. You have gone to an airport and there is an immigration check over there. So you have to go through a door where they check all your they put yourselves in a x-ray machine. So just imagine that behind you there are 50 people standing and you all are trying to go through that door. So when you go through that electric x-ray machine that is in a square shape, so your movement is getting blocked, right? So what happens is that when your movement is getting blocked, that itself is called resistance. In an electric wire, as I told you earlier, there are many electrons moving randomly over here and there. So what happens that when the electrons move and they get an obstacle, a collision, that is called resistance. So that is electrical resistance. You can picture yourself as an electron and behind you there are 50 to 20 electrons coming through a door, and that door is called resistance. When all of you try to go through that same door at the same time in the same direction, electrical resistance, you can compare that with the electrical resistance. So let me read it out once again. Electrical resistance is measured is the measure of stopping electrons flowing. So you can see over here there is a cell 1.5 volt and there is a lamp or a bulb. So as we have already seen earlier, there was something flowing through this so that the current glows and there is a light energy given out. So when charges move, the charges move inside the copper wire. The copper wire, there are many electrons. Let me give you an explanation showing you a diagram. This is what happens in a copper wire. You can see we have zoomed 2000 times inside a copper wire. Copper wire is the thickness of my hair. So we have gone inside. This is an electron microscope. Just imagine you are seeing an electron microscope and you are seeing here dots represent charges, and these are the plus symbol. What you have seen over here is the cations. So what are cations? I'll tell you. Just remember, these are cations and the electrons are freely moving randomly in all directions. So this is a copper atom over here. You can see this is a copper atom. We have seen earlier that there is one electron in the outermost orbit. So these one electrons are responsible for the charge, right? So these electrons are called valence electrons and they rotate, revolve around the nucleus. So what happens is that when they are freely moving inside the copper wire, as you can see over here, electrons are moving randomly over here and there in all particular directions with all particular velocities, right? So these, I have removed the cations and just you are seeing the electrons out here. So electrons are moving randomly with all possible velocity in random direction. When we connect a battery or a cell over here, you can see they are moving in a particular direction. So when they move in a particular direction, they face resistance. That resistance itself is over here. These cations are those where the electrons they move outside. These copper atoms itself get a positive charge. This positive charge is called cations. Okay, so you have seen over here in the electron microscope what is happening is that these cations and the electrons, they are freely moving, and when we connect a battery source, there is a movement of the charges in particular direction, and the resistance Electrical resistance can be easily considered with an example. What is electrical resistance? We have drawn a diagram over here. If you can see over here, there is a small beaker. Here and here there are similar beakers, and the level of water you can see it is one and the same. There is a small tap connected, right? Here also there is a small tap connected. There is only one difference you can see. Here in the second beaker there are small pebbles over here, but there are no pebbles over here. What happens is that if I open this tap, what will happen? Water will flow easily and it will be going outside, right? So when there is no resistance, the water freely flows, and that too high amount of water will go out of the tap. We can correlate water flowing with the current flow. Here you can compare the level of water as the voltage or the potential difference, and the water flow, what is flowing outside of the tap, you can compare that with the current. And there is no resistance. See, the water resistance is minimal out here, so we can compare that with the resistance of wire. So what happens is that higher the water flow, higher the current, and both the sides the water resistance will be low, and the resistance inside will also be low. So this we can give an analogy. We can see that these are the same we can see in a conductor. Metal conductors, if you can see, this is a metal wire, this is a metal conductor. What happens is that there is low resistance, very low resistance inside, so current easily flows through the metal wire. Now what happens is that we have taken another beaker, similar beaker, right? But here the only difference is that there are some pebbles inside. When there is a pebble and I am trying to open the tap, water is coming over here, water wants to go outside the tap, but due to this blockage out here, due to this resistance, water doesn't flow outside. It drops, water drops, drops are falling. It doesn't flow like the freely flowing out here in the top. We have seen that water was freely flowing out here. So here the water flows one or two drops at a time. So there is resistance is very high. Water is slowing. We can take this analogy as water slows because of high resistance. So inside this there is a potential difference, voltage. Voltage remains the same in both the cases. Voltage is compared to the level of water, and the resistance, the water resistance is very high out here. So the resistance we can compare that with we can put an analogy saying that if there is very high resistance, so we can get the low water flow, and the water flow we can compare to a current, so we get small amount of current. This you can compare with an insulator. Insulator, what happens is that this is an insulator. This doesn't, if you pass current through this, there is no current coming out. It is very bad conductor, we call this is a bad conductor of electricity, and this metal wire is a good conductor of electricity. This is due to this reason. The resistance is low and the current flow is high inside the metal wire. Here the resistance is very high and the current is minimal, so you don't get current outside here in the insulator. Now there are two properties out here. So for the resistance, as you can see over here, there is a diagram drawn. There are two properties of resistance. Once the resistance, the length of the resistance is increased, right? This is L. We have taken another resistor where the length of the resistance is more. So the length of the resistance is directly proportional to the resistivity. Okay, this R represents the resistance and L is the length of the resistor. Here it is increased, so the resistance also increases, the length of the conductor also increases. Now there are two properties out here. So for the resistance, as you can see over here, there is a diagram drawn. There are two properties of resistance. Once the length of the resistance is increased, right? This is L. We have taken another resistor where the length of the resistance is more. So the length of the resistance is directly proportional to the resistivity. Okay, this R represents the resistance and L is the length of the resistor. Here it is increased, so the resistance also increases, the length of the conductor also increases. So the more distance you are traveling, the more resistance is coming. So here there are less distance you have to travel yourself. You are standing on top of this, and you are traveling from here to there. So there is less distance to travel. Here you have to, if you start walking from here to here, you have to travel, compared to this you have to travel more distance. That is the analogy out here. So resistance increases because the length of the resistance increases. This is the first property of resistance. Then we have a second property out here. Imagine a resistance, and you have cut open the resistance. Once you cut open the resistance, you have broken into two halves. So this is called a cross section area. Imagine one charge passing through this cross section area. In actual case, this is extrapolated. As you know, only one charge doesn't pass through this. Just for simplicity case, we have taken only one charge passes through this cross section. If the cross section area increases, suppose this big resistance resistor is taken and you cut into two halves. So compared to this cross section area, this cross section area is more, right? What happens is that more number of charges will pass through this cross section area. So what is happening is that, see, R is represented by the resistance, and it is inversely proportional to the cross section area. This is the cross section area. So cross section area, see, it is increasing due to you can see the cross section area increasing out here. So resistance is inversely proportional to the cross section area. So these are the two properties of resistance. First is directly proportional. Directly proportional means when this increases, this has to also increase. For example, when the resistance is 5 ohm, the length has to increase. So that is called directly proportional. Inversely proportional means when the resistance is increasing, the cross section area is decreasing, and the more the cross section area, the resistance is less. That is called inversely proportional. So you can see out here what is directly proportional and inversely proportional. Let me tell you once again. Resistance is directly proportional to length, and resistance is inversely proportional to the cross section area. Okay. So as we have discussed earlier, you have seen out here, this is a copper atom, and there are free electrons out here. This outermost orbit, you can see one electron. This is the electronic configuration. First orbit 2 electrons, second orbit 8 electrons, third orbit 18 electrons, and for fourth orbit, last orbit, we have one electron. This is loosely bound electron, and this is responsible for the charge. Once there is a voltage source connected, the electrons or the charge, they move in a particular direction. This movement of the charge in the particular direction is stopped by the resistance, and we get that electrical resistance. Electrical resistance is the measure of stopping electrons flowing. So this is the resistance part of it. Hello students, my name is Reni, and this is a GCSE video. We will be talking about electric current. So what is electric current? Electric current is, we can easily compare with a water flow. When water flows from a higher level to a lower level, when water flows, it it flows from a higher potential to a lower potential. So here the water flow can be compared to an electric current. Electric current also flows from a higher potential to a lower potential. That was the thinking in the 17th century, and will we still go as far as the electric current is concerned, from positive terminal to the negative terminal. So that was the thinking of the 17th century scientists, Benjamin Franklin and other scientists. They did lot of research and they concluded that current travels from the positive terminal to the negative terminal, and we still believe that, and we call it the and the bulb. So you are already aware that there are some wires, and wires, inside the wires you need to go, because that is where the electrons are. So I will be taking an example of a copper wire. So copper, you are already aware of copper. Copper, if you have studied chemistry, copper electronic configuration, I'll just write it down. This is protons. It consists of protons and electrons. This is the subatomic particles, and protons have positive charge 1.6 into 10 raised to minus 19 coulomb, and electrons 1.6 into 10 raised to minus 19 coulomb. You can see both values are same, but the charges differs. One is positive sign. This is stationary in the nucleus, so it doesn't affect the current as far as electric current is concerned. So we will not be going much. We will be discussing about protons because it is very stationary inside the nucleus. We will be that flow. So electric current can be given by the formula total number of charges in a particular certain time. So charges divided by time. That is the formula. Electric current is represented by I. Charge is represented by the word letter Q, and time is represented by T. So you can see over here, this is the formula where we can calculate the charge. Let us assume an electric heater. This electric heater takes an current of 25 amperes. Amperes is the quantity over here. Coulomb by second was derived and given the name ampere. Ampere is the name of the famous scientist who discovered all the electric effects. And Coulomb was one of the famous scientists also who discovered about electricity. So that is why they gave the charge the abbreviation of Coulomb. It is represented by Q, and time is represented in seconds. So here the charges, Q is equal to current into the time. So if you can see over here, it is 25 amperes multiplied by 80 seconds. In 80 seconds the water boils. So that is why we can calculate the charge. So the charge is equal to the current into the time. And second example we can take where in a toy plane, it flies and completes a lap of 2 minutes. So in 2 into 60 seconds is the time. Q is equal to 3C. 3C means 3 coulombs. So I, if you can see this formula, is equal to Q into the time. So you can calculate the current flowing through this plane by using this formula. As you can see, the charge carriers over here is due to the current flow. In the nucleus there is protons as well as electrons. These electrons are having negative charge, and these protons having a positive charge. The charge is calculated to be 1.6 into 10 raised to minus 19 coulomb. You can see over here protons, they have positive charge. And a brief about what are charges. Charges is the total amount of current what is passed through in a certain time period. So this can be quantified using this statement, where charge is represented by capital Q and current is represented by capital I, and within a time period is represented by a small t. We can use this equation. Current is equal to charge divided by time. What is exactly is current? Current is the flow of charges in a certain time period. You can take an analogy. Analogy in a sense, you can compare water with the water flow with the current flow. In 17th century, the conventional current was determined by scientists Franklin, Benjamin Franklin and other scientists. What they thought was current always flows. The water current always flows from a higher potential to a lower potential. That is why they told that if this is a cell and this is a lamp or a bulb, current flows from the positive terminal to the negative terminal. That is what they thought for over a century. In 18th century, what had happened is that in 18th century, Sir J.J. Thomson and other scientists, they discovered subatomic particles. What exactly is subatomic particles? I'll give you a brief description. So subatomic particles consist of three particles, primarily three particles: electrons, protons and neutrons. As you are already aware, if this is the atom according to Bohr's model, this is the nucleus. Nucleus consists of protons and neutrons. Neutrons don't have any charges, and protons, they have positive charge. You have seen over here. But this doesn't come into the picture in the electric current. Why? Because current is the flow of charges. So nothing flows inside the atom. Because this is stationary, neutrons and protons are stationary, we will be primarily discussing about electrons. Electrons are responsible for the flow of current. So that is why electrons are called charge carriers. Charge carriers, why? I'll give you a brief description. What happens in an atom is that, as you can see over here, there are wires connected. I have not drawn over here. These are wires connected. So these are primarily copper wires. If you can see inside the copper wires, if you can zoom into the copper wires, what happens is that there are free electrons. What are exactly free electrons? I will be telling you. You can see the structure of copper. There is one electron in its outermost orbit. This is called valence electron. What happens is that this valence electron is responsible for the flow of current, which is called charge carriers. This loosely bound atom, it rotates, revolves around the atom. So what happens is, because since it is loosely bound, some additional energy is given in the form of heat or light or whatever the source of energy is. This electron moves away from the atom easily. So these kind of electrons are freely moving, you can see inside the copper wire. So these are called charge carriers. So what happens is that when you connect a battery, a voltage source across, this is the positive terminal, this is the negative terminal. You can see what happens is that electrons are electronegative. They are flowing towards the positive terminal. So that is why what the 18th century scientists, they proved that electric current is primarily due to the flow of electrons. This you can see how it is moving towards the positive terminal of the battery. This is the cell where this is the positive terminal and this is the negative terminal. So this is how the current flows. The copper atom, where the first orbit consists of two electrons. You can see there are two electrons. Then there are second orbit, there are 8 electrons. You can see there are 8 electrons in the second orbit. In the third orbit, there are 18 electrons. And in the fourth orbit, that is the last orbit of the copper atom, there is only one electron revolving round the nucleus. This is the nucleus where the protons and the neutrons are situated, and the electrons revolve round the nucleus. So the fourth orbit where there is only one electron, that electron is loosely bounded, and when there is an external energy or a heat given to the electron at room temperature, it freely moves around the copper wire. So this is a copper atom and this is a copper wire. You can see the electrons freely randomly moving in all particular directions in all particular velocity. This is the view of the electron microscope. If you zoom into a copper wire that is the thickness of a human hair, you will see cations and the electrons. You can see small dots, that is the free electrons roaming randomly here and there, and the positive charge you see over here is the charge of the atom. When the electron over here leaves the outermost orbit, the copper atom gets a positive charge. So all these positive charges over here, the cations, are the copper atoms where the electron has uh, been removed from the outermost orbit, and it is freely roaming here and there at room temperature within the conductor itself, within the metal here is considered as a copper wire. So suddenly uh, when there is a voltage source or a battery connected across the copper wire, you can see what is happening is that since electrons are electronegative, it tends to move from towards the positive terminal. So you can see they are moving in a particular direction. So this is called the electromotive force. What happens is that electrons is pushed to the positive end of the cell or the battery. So this is the concept behind the electromotive force of the cell. Good day students, this is Reni and we will be talking about the voltage difference, and today we will be speaking about what is capital V. It is called voltage difference. So before going into the details of the same, I will try to explain through an illustration. Over here there are two breakers. You can see one is in high altitude, and the second beaker B, it is in lower altitude. So you are already aware, once the water is filled in beaker A, the water flows from the beaker A to beaker B, right? It flows from beaker A, and the level of water, you can see it is slowly coming down, and the water flows from higher potential to a lower potential. So this is the concept behind what is potential difference. The concept here remains the same. Here the water flows from high potential to the low potential. You already seen that. So what is happening is that we are talking about voltage. So voltage comes as far as current is concerned in an electrical circuit. So what is a V, capital V voltage? It is the potential difference. The potential difference is high potential and the low potential. High potential we abbreviate as a positive, and the low potential as a negative. So here there is a potential difference created across, which brings the current I. You can see over here the current I is abbreviated over here. So what brings the potential difference is that once the potential difference is created, once there is a positive high potential and a low potential, accordingly the potential difference gets created. It brings a current in the sense there are charges flowing inside the metal wire or the metal conductor. So the potential difference brings the current, okay. And the battery, here the battery is more than a cell has 1.5 volts, and battery should be more than 3 volts. If it is 3 volts, again it is called a battery, and if it is more than 3 volts, it is called a battery. So the battery possesses potential difference V. Okay, so battery is the main source of potential difference, that you need to remember. Battery also displaces the electron in one particular direction. We will be giving that with example over here. So how it moves the electrons in a particular direction. So we have seen in the video wherein we have taken an example of a copper wire, and we have seen the freely moving electrons moving to a particular direction over here. So this same direction the battery is displacing the electrons, whichever the electrons are passing. The electrons are charge carriers, you remember, right? Electrons are charge carriers, it moves in a particular direction. So this direction of displacement is primarily due to the battery, and battery has potential difference, and it creates the potential difference. Once it creates the potential difference, accordingly I is generated, current I is generated. So this is the copper wire where freely moving electrons are there, and you have seen there are cations and there are electrons freely moving randomly at different velocities. So once a battery source is connected, it moves only in one particular direction. That is what it is written over here, only in one particular direction, and this is called EMF of the battery, EMF of the cell, electromotive force of the cell.
Hello students, my name is Reni and we will be discussing about potential difference. What is potential difference? If you can see out here, it is mentioned potential difference brings current. How? Potential difference you can visualize like you have two beakers and one beaker is in the top end and one beaker is in the bottom. These two beakers will have a certain amount of water inside it. So what happens is that what is on top, the water on top will flow from top level to the bottom level, right? If there is a connecting tube between these two beakers, and the water will always flow from the top level to the bottom level. This top level in physics, it is called higher potential. This is an higher potential. The water flows from a top level, so it is called a higher potential, and the lower potential is the potential which is as at the down level, it is called the lower potential. So what happens is the water flows from a higher potential to a lower potential. That is the simplest how we can visualize what is a potential difference. So if there is a potential difference created within a circuit, so it brings out current, and current brings out charged particles, and charged particles will give you current. Okay, so that is how the first statement goes. And a battery, you can see over here, battery possesses V. What is V? V is the potential difference itself. A battery is the togetherness of two or more cells. 1.5 volt cell is there. If you connect 1.5 volt plus 1.5 volt, it becomes 3 volts. So what happens there, 3 volts and more than 3 volts is called as battery. So battery always possesses within itself a potential difference, and this battery itself, it is a driving factor which creates the potential difference inside the electrical circuit. The battery displaces the electron in one particular direction. If you can take one battery, a pencil cell, what happens is that in that cell it is clearly written, if you see the downside, it is clearly written that there is 1.5 volts inside the battery. So 1.5 volts, what it determines is that 1.5 volts potential difference it can bring if it is brought through a electrical circuit. So if 1.5 volts is brought to an electrical circuit, it can create 1.5 volts potential difference in that particular circuit. So battery has a phenomenon which displaces the electrons inside in a particular direction. How it happens we can see just now. If you can zoom into any of the metal insulator, what happens is you can see the electrons moving randomly in any particular direction. There is no fixed direction, you can see over here. There is something called as cations. So what is cations? Before telling what is cations, I would like to take you through a tour of an atom. what happens inside an atom. Copper is represented by, this is the electronic configuration of copper, and this is the atom, copper atom. What happens is that this copper atom, you can see this copper atom has 2 electrons in the first orbit. In the second orbit it has 8 electrons, and in the third orbit it has 18 electrons. But we are only interested in the final orbit. What happens in the final orbit? You can see only 1 electron is moving out here. What happens is that this 1 electron is loosely bounded electron. So this loosely bounded electron, one electron, it moves out of the atom freely at room temperature. Okay, so what happens is this becomes no more associated with the atom. It is called a free electron. This is the photo what we draw out the free electron. This is what we had seen earlier. Free electrons are there inside the insulator, right? So these are the free electrons. So coming back to what is cations, once these free electrons moves out of the atom, any atom, if an electron is moved out, that atom becomes positively charged. Why? Because it is deficient of electrons. So how many atoms moves outside, that much charge, positive charge, this atom will have. So 1 electron has moved out, right? So what happens is that one charge will get 1 charge, positive 1 charge. So that is what we have drawn over here. This is the cation. Cations are also there. So these are all the cations. That means all 1 electron of copper has already moved out of the outermost orbit, and it is roaming here and there, you can see. So if you merge these two figures, the cations and the electrons, you can see a jumbled figure. This is the inside of a conductor. This is the what happens deep inside the conductor. So there is a chaos, right? Electrons are freely moving inside the conductor, insulator. So this picture we have drawn out here. If there is no battery, this is battery source connected. If there is no battery, electrons, free electrons will move randomly, like over here, in all particular direction. As soon as we connect one battery source, this is the positive terminal, and this is the shorter terminal is the negative terminal. So once we connect the battery source, what happens is that all electrons move in one particular direction. This particular direction over here it is mentioned, and we call it in physics language electromotive force of the cell. So this particular direction, the battery is responsible for the flow of electrons in one particular direction, because before connecting this battery, these electrons were roaming here and there at random velocities in room temperature itself. As soon as the battery is connected, these electrons move towards the positive terminal. You can see the bigger line shows the represent the positive terminal. So what are things we have learned from here? We have learned that potential difference brings in the current, right? If water flows from a higher level to a lower level, it will be flowing a path of higher potential to lower potential. So potential difference always brings in a current inside a electrical circuit. Battery processes potential difference V. Okay, it is termed by the alphabet V, and we have already seen that battery displaces electrons in one particular direction. We have and it is called electromotive force of the cell. So this is what I wanted to say. This is Reni signing off. Thank you so much.